Hi, I'm Chloe, and today I'm going to do this control volume analysis problem. So this problem says oil flows through the 8-inch diameter pipe with a velocity of 18 feet per second, and it discharges into the atmosphere through a nozzle. So determine the total force the bolts must resist at the connection AB to hold the nozzle onto the pipe. And it gives us gamma equals 55 pounds per feet cubed. Okay, so to start off this problem, I just drew the control volume, which is just this area in the nozzle here. And then I went ahead and drew the normal vectors going off of either side. Okay, so then we're gonna look at our assumptions next. So for this problem, we're going to assume steady, incompressible, inviscid flow. So the density is the same throughout and it does not have viscosity. And then I just went ahead and rewrote all of our dimensions so that they would be in the same units. So our first diameter 0.667 feet, our second diameter 0.333 feet. Velocity 1 is 18 feet per second, and then we know that our specific gravity gamma is equal to rho g. Okay, so for the first step, we are going to do mass conservation. So I went ahead and wrote out the integral here, and as you can see, we can cancel out the first part of the integral because we are assuming steady flow. Okay, so then we'll split this part up into the flow in versus the flow out. The flow in is going to have a negative sign because we see that the normal vector and the velocity vector are going in opposite directions. Okay, and then the flow out is going in the same direction as the second normal vector. So then that one's positive. All right, and then we can just expand this and we are going to get that this integral gives us that u2a2 equals u1a1. So if we rewrite this a little bit, we find that u2 equals u1 times the area ratio of a1 to a2, which we can simplify to diameter 1 squared over diameter 2 squared. All right, and from this, we will get that our velocity going out of the pipe or out of the nozzle is 72 feet per second. All right, so then our next step is going to be to use Bernoulli's equation. So I just wrote this out here. Since this is moving along the x-axis, there's no change in y, we can ignore gravity. So we're going to ignore the z terms in this equation. And I'm going to assume this problem in gauge pressure. So then we can say that P2, where it's discharging into the atmosphere, we can just call that 0 at atmosphere. So then when we solve for P1, that will be atmospheric pressure. All right, so then we can just plug in all of our numbers and we can solve for, don't forget, rho oil we can find because we are given specific gravity right here. So rho is just going to be gamma over g, and g in this case is 32.2 feet per second squared. All right. Okay, so then we're just going to follow this out and we will get the P1 equals 4,151 pound per feet squared. All right, next we are going to do the momentum conservation. So I went ahead and wrote out this integral, and then we can once again cancel out the first term because it is steady flow. All right, now for the net forces, we know that the net forces are the sum of the pressure force, the shear force, force due to gravity, and external forces. In this problem, we only have pressure force because there's a change in pressure, and external forces, which is what we're looking for. And these external forces are going to be the same forces that are on the bolts, which is what we're looking for. Okay, so once again, we can rewrite this integral. And so the signs here are going to be a little bit different. And this is because the flow is in the negative x direction. Okay, and as you can see, we have u dot n inside of the integral. And so u dot n times u is going to give us u squared, but then it's going to be a little bit different due to the signs And so we're going to have that U1 times U1 dot N is a positive 18 squared, and U2 times U2 dot N, that's N2, is going to be negative 72 squared. All right, so we can just plug all of that in, and the pressure force simplifies. The integral from the pressure force is P times the normal vector dA, which will simplify to P1A1, because that pressure we solved for is on the right here, where it's going into the nozzle. Okay, we found rho above from specific gravity, and then we can simplify, since we have the U's and the A's, we can just simplify that to Q1 and Q2, the volumetric flow rate, and that'll all be times rho. Okay, so then here we're just gonna plug in all of our numbers and solve for the external force, and we will find the external force to be 869.3 pounds. Thank you so much, and I hope this helped.